Hello again. In this second tutorial, you'll learn how transition goals are formulated and some of the basic economic concepts used in integrated assessment models. So the responses that these models propose are a massive transformational effort. To situate ourselves and motivate us to consider the scale of these efforts, let's remind us of the similarity massive transformations have taken place in our species' history. So 7,000 years ago, we stopped moving around and started growing stuff. Then about 300 years ago, we industrialized food production and started fabricating stuff. As a result, our population has exploded and now seems about to crest for seemingly benign reasons like access to contraception and education. In an idealist projection, we're about to transition now to a sustainable mode of living within planetary limits. This would allow us to maintain something close to our current population. That picture, however, ignores that we're rapidly entering a climate emergency. That's likely to be so destabilizing that there will be a significant population drop this century. Some even think we might be headed for collapse. Now, in any of these three cases, we shouldn't downplay that we live in a critically important time in our species' history. Each one of us alive today plays our small part in seeing our species through this critical period. So before we start seeing plans of what's feasible, let's talk about what needs to happen. So we can use the causal chain that ends in climate damage as a guide. This starts with fossil fuel production that feeds energy consumption, that produces greenhouse gas emissions, that trap heat via their forcing effect. This heats up our environment, and finally generating the damages through effects like extreme weather events. Okay, so let's look at projection of future climate damages and how we can reduce them. The goal is to stay out of the region of high climate impacts shown here by the high intensity of red. That's where we're headed currently because we're still emitting large amounts of greenhouse gases from burning fossil fuels every year. The first and most important thing we need to do is to cut those emissions to flatten the impact curve. This can be done through demand-side mitigation that reduces consumption and supply-side mitigation that lowers the emissions intensity of consumption. The reality is that there's so much greenhouse gas in the atmosphere already that even with our best mitigation efforts, it'll probably level out too far in the red zone. This means that we'll also need to remove large amounts of greenhouse gases to get back down to a level of damages that's manageable in the long run. Emissions removal, or so-called negative emissions technology, might be able to eventually restore the balance, but these technologies are unlikely to ever scale up or soon enough to prioritize them right now. So the damaging impacts will likely exceed what we can tolerate for some time to come. We then need stopgap measures that temporarily cool the planet to keep us out of the red zone in the meantime. These are things like solar radiation management that, for instance, would reflect the sun's radiation out into space before it converts to heat and has a chance to get trapped. Then finally, we'll do what we can here to limit the damaging effects of warming by adapting. This can be done in place, like with temperature-controlled environments and heat-tolerant crops, and by moving humans and food production, as well as natural and physical capital, to less affected areas. Stepping back, note that this picture of the physical goals in the problem is actually ambiguous about the socio-economic paths we take to realize them. That path is laden with choices about what we value. So a prescriptive goal is one that also specifies the socio-economic trajectory, and that's where economists and finance people come in. In ideal settings, they consider what are called optimal plans by asserting what constitutes a desirable socioeconomic trajectory. In one approach, they set up an optimization problem whose solution is an optimal economic plan that achieves the most desirable trajectory within the stated constraints. So the commonly known formulation of transition goals is called net zero. This is a goal state in which our society emits no more greenhouse gas than it removes each year, so we are at least not making the problem worse. To keep it simple, the policy here consists of two kinds of actions: mitigation, where we work on restoring the energy balance, and adaptation, where we work to reduce expected harm from current and future effects on climate. So for the sake of reasoning about possible transitions, let's plot mitigation and adaptation risk as two orthogonal axes. Now, any plan that gives a risk level for each can be plotted as a point in this plot. Let me emphasize that there is no option not to transition to a net zero state. What we're concerned with here is what the rest of the world is like in that net zero state. At one extreme, we let climate disaster run its course, and the net zero state is achieved by the decimation of our civilization. That puts us here, where we've chosen the maximal adaptation risk. Alternatively, extreme mitigation, like instituting an immediate moratorium on the burning of fossil fuels, would land us somewhere up in this corner. That would decimate many industries and would also wreak havoc on society. And so it's the economic shocks as we move on paths that get too far towards either of these extremes that economists want to avoid. So bureaucrats came up with the term ordered transition for the Goldilocks pathway that optimally trades off between the two risks. For instance, we want companies and nations to have time to plan for big changes like the birth and death of whole industries in advance, rather than at the moment when damage shocks spontaneously happen. Another more subtle benefit of a planned transition is that we can exert more control on which and where the remaining affordable oil is used, and an ordered plan tries to do that. All of these approaches require us to put a value on future states of the world and the actions we take under policies that get us to those states. So how do we do that? Let's go over the kinds of optimizations that economists use to produce distinct plans, each optimal in their own way. So the policy here is set by the level of mitigation M. Mitigation demands investment, for example, the cost of building the infrastructure for renewables. So that's one component. Another component is the damage function, which is a function that maps changes in temperature to associated damages in the fraction of GDP destroyed. These will tend to rise with temperature. So by lessening the increase in temperature, the benefits of mitigation are that it leads to reduced climate damage. So the first kind of optimization is thus a cost-benefit analysis in which we maximize the macroeconomic value, which here is just the difference of the benefits and costs, which tells us what the optimal level of mitigation is, here M star. But costs and benefits may be hard to quantify since the systems that produce them arise from many interacting socio-economic variables. Regardless, we're also faced with an intertemporal choice problem of how decisions now affect cost and benefits later. To handle this, the microeconomic approach instead uses the decision theory solution to go from consumption, which is assumed to have an intrinsic perceived value, to an individual, to a value or welfare function that's maximized over the policy space. I'll explain what goes into a value function on the next slide. Finally, as a third possible formulation, what if all we want to do is avoid excessive damage? This is called a cost effectiveness analysis because we look at the cheapest mitigation plan that's consistent with temperature not exceeding some fixed bound that we decide to impose. This analysis, which you'll find in the IPCC, doesn't take into account the damages below the temperature bound. Cost-benefit analysis and a cost-effectiveness analysis can actually be combined as well. So stepping back, you can take away the fact that each of these problem formulations can actually give a different solution to what the best plan is. The same is true with definitions of value. In decision theory, where the mathematics of planning is formulated, value is often quantified as the expected discounted return. Let's break that down. So there is, of course, the most important choice of how to define welfare or utility. Is it really based on consumption? What if we could quantify happiness? What are the problems with that? With what utility means to an individual, we then need to decide how to combine the utilities of distinct agents, like countries or demographic groups in the world, into one single value. These kinds of functions are called social welfare functions. We also need to parameterize the plan. What is it that we can actually change in the world? What are the knobs that we can actually control? For each agent included in the social welfare function, we need to calculate their utility or their benefits and costs, and then estimate the sum of what these will be into the future, the so-called return. The estimation of return has some uncertainty associated with it. One choice is to look at the typical case, which is just to take the average over this uncertainty. Keep in mind, though, that there are alternative statistics that aim to better capture the risk in the extremes allowed by this uncertainty. Uncertainty typically grows the further into the future we predict, and that's one motivation given to justify scaling down how future benefits contribute to the value relative to current benefits. Called temporal discounting in economics, it's done by setting an effective time horizon beyond which benefits and costs are effectively ignored. So now let's move on to looking at integrated assessment models that typically use some kind of cost effectiveness and welfare maximization component. So establishment economics finally integrated a model of the climate with models of the economy in the context of climate change about 20 or 30 years ago. These are called integrated assessment models, even though they don't really assess, rather prescribe what to do by defining control knobs and finding their optimal positions. The economy component centers around a damage function that maps temperature changes to climate change damages in economic units like dollars. This component is then outputs the amount of the emissions from production. These models also have a climate component that centers around climate sensitivity, or how temperature changes as a result of the doubling of CO2. This integrated approach of these two modules suffers from a host of methodological issues and questionable assumptions that make it much less reliable than the climate modeling alone. Some prominent economists think the approach is so flawed it's disingenuous to promote its use in policy, while some of these criticisms come from a larger debate within the field of economics about whether and how to incorporate individual behavior into models of aggregate economic activity. Other researchers, however, take a more pragmatic approach of just trying to improve the existing models. Okay, let's look at a bit of a taxonomy of the different types. So, integrated assessment models are essentially macroeconomic models with a climate module appended to them. And they formulate a mitigation policy, as for instance, in the level of emissions abatement. So the standard integrated assessment model are general or partial equilibrium models, where equilibrium here means that they assume a fast dynamics to justify using functional rather than coupled dynamic relationships between some variables. Partial or general is about how geographically aggregated are the variables. There's also some newer generations of models which adopt methodologies from economics, like computable equilibrium models that include more realistic pricing dynamics, or dynamic stochastic general equilibrium models that include random economic shocks. So finally, agent-based models are a distinct class that have no so-called structural component, that is, where there's no parameterized macroeconomics. All macroeconomic phenomena are emergent from the collective behavior of the low-level agents in the model. This is still a field that's under development. Okay, let's look at some of the shortcomings of modeling practice in integrated assessment models. So maybe the most egregious is the damage function incorporated through a methodology that has some issues. So they are inferred from geographic and historical variation. So for instance, shown here. And it's unclear if the temperature-dependent damages that dominate in this type of data, historical data, have a similar dependence as those that will dominate in the future as climate change reshapes society and the planet. It's understandable that estimates shift as knowledge deepens, but these socioeconomic models the estimates that they give seem to lag rather than lead in policy. So for example, the temperature that these models say are consistent with maximizing social welfare as they've defined them, so that's on the y-axis here, these are the dots of the estimates in black. These are typically higher than the temperatures that are the stated goals in prevailing policy. So this is the green here. So this all suggests that models are actually less impactful than you might think. So up to recently, integrated assessment modeling didn't really handle uncertainty at all, nor the known climate feedback mechanisms that could make climate change drastically more costly. These kinds of risks have been clearly stated for over a decade, so it's not like there wasn't the time to develop them. This is a paper from 2009. For instance. So then there's also all the issues that integrated assessment modeling inherits from just the issues in economics proper. So things like assuming rational behavior of agents, these equilibrium assumptions, And in particular, IAMs don't tend to have models of money or finance or banking, so how pricing of various commodities fluctuate. And generally, there seems to just be much less empirical validation in the modeling practice. So it seems like econometrics and predictive finance as fields apart from climate don't even use these kinds of models when doing their own projections, though there are some exceptions, like the European Central Bank. So is there any better approach to making climate economy projections that's currently available? Well, Robert Pindrick, who's an MIT economist, quite critical of integrated assessment models, proposed relying on experts instead. He's solicited estimates from both climate scientists and economists regarding, for instance, the social cost of carbon, with the distribution of estimates from the experts shown here in these bar graphs. And that's social cost of carbon is just how much a unit of emission costs in lost consumption. And perhaps not surprisingly, climate scientists gave larger estimates than economists did. So clearly personal bias and what experts' training is going to negatively affect how reliable expert solicitation is as a methodology for coming up with this. And the IPCC's approach that we'll see in the next tutorial attempts to address this using narratives, which we'll see. Okay, so how sensitive are these integrated assessment modeling results? Now you're actually going to go head to the computational part of the tutorial to see how sensitive on certain key parameters the results of a simple integrated assessment model actually are. So you'll look at the utility function, temporal discounting, and damage functions. And to summarize this video, we've seen that IAMs involve hard science and ethics that are limited in many ways. They generate socioeconomic projections by transparent assumptions that we can improve. Incorporating climate feedbacks and social welfare functions are two areas of current improvement. And I'm sure we all hope that this kind of progress accelerates. So in the next tutorial, you'll see what the IPCC has managed to do with these integrated assessment models so far.